Question 2 then introduces the Boltzmann distribution. Boltzmann's huge contribution, remember, was recognising that chemistry is all about statistics, that in a pot full of gas, for example, the molecules aren't all travelling at the same speed. It's not as simple as that. There's a distribution of speeds, and the speed of any individual molecule will constantly be changing as it collides and either loses or gains kinetic energy as it collides with other molecules. And he figured out what the statistical distribution of energies would be as a function of temperature, and that holds the key to all kinds of things in physics and chemistry, including understanding rates of reaction. So that's why these distributions are so important. Okay, so you need to be comfortable with that idea that what this is all about is that not all of the molecules in a gas or a solution have the same energy as one another, but the distribution of energies remains constant with time unless there's a reaction happening. Okay, so when you draw a Boltzmann distribution, the first thing is you've got to make sure you label the axes. So it's energy along the bottom. You can write kinetic energy if you want, although in fact the Boltzmann distribution applies with other kinds of energy as well, but you can write kinetic energy along the bottom if you prefer. And on this axis we normally just write number of molecules, which seems slightly mysterious, but in reality it's a statistical thing called the probability density, but we're not getting into the maths of that, so we're just simplifying it by writing number of molecules like that. And both of these scales are starting at 0, so you probably don't absolutely have to do that, but it's a good idea to make it clear that that's the origin. Because one of the important features when you come to draw these things is that you have to establish that 0 molecules have 0 energy. In other words, no molecules are absolutely devoid of energy. And that needs to be clear when you draw the diagram. So it means when you draw the curves, they must start there. If you have curves starting up here somewhere, then that will be wrong. So the general shape is an asymmetric curve. So it looks kind of like this. Okay, so don't aim for a bell curve. It's not meant to be symmetrical. It tails off more gradually in this direction, and you normally sort of draw it something like that. The reality is that it's asymptotic to this axis, which means that it gets closer and closer and closer to that axis, but never quite meets it. Obviously on the scale you're drawing it, eventually it would appear to merge with it. But what the exam board says, which I don't particularly think I agree with, but nevertheless what they tend to say in the mark scheme, is that this curve must not touch the axis, because they just want to be clear that you understand that it doesn't kind of slam down into it. So when you're drawing it, don't sort of say, well, you know, at my resolution you can't tell, it's not quite touching it. And try and hold out for that, because yeah, you can challenge them in the High Court, but it's easier just to, you know, just to make sure that it sort of comes down to there, but you don't grapple with the issue of what happens when it gets really, really close. And the idea is that if you change the temperature, then that distribution changes. It will still have the same shape qualitatively, but it's going to be shifted. Now the first thing, which is the most obvious thing, is that common sense tells you that if the temperature is higher, then on average molecules will have more energy. You know, put in energy, the temperature goes up, therefore makes sense that the molecules on average must have a higher energy, and that means the position of that peak will be shifted over in this direction at higher temperature. What's less obvious, but just as important, is that the area underneath this curve, so in other words the area between the curve and the axis there, that represents the total number of molecules. And if you're looking at the same population of molecules, therefore at the two different temperatures, that total number is still the same, and therefore the areas underneath the curves have to stay the same. Now they're not going to, you know, measure it with little squares and check whether you've got that right. This is just a qualitative thing, but the consequence is that if the peak shifted this way, meaning that it's more spread out in this direction, it has to be squashed in that direction. Otherwise, the areas wouldn't be the same. So when you draw it, the two things you have to make sure are clear is that at the higher temperature the peak is shifted further this way, but that the consequence of making that change is that it has to be more squashed in that direction. So you're going to get something that looks like this, still starting at the origin, must start at the origin, but make it very clear. You know, don't just shift it a millimetre to the right and expect them to get their rulers out and check. You know, it needs to be clear difference that this peak is significantly further to the higher energy side at higher temperature, but the consequence is that it needs to be shorter, because basically what we're saying is the area of that bit has to be balanced by the area of this bit, so that the two areas under the two curves could reasonably be seen to be the same. And obviously make it clear which one is which. So this is the high temperature one, and that's the lower temperature one. And then it asks you to mark on the activation energy. So the activation energy is just a fixed value of the energy. Okay, so the activation energy, you just draw a line, and you can draw it in principle anywhere, but for most of the reactions that we're concerned with, it's towards this end of the curve. So usually you sort of draw it here somewhere, and you say, right, this is the activation energy. Okay, so those were the features you needed to have to get all the marks in 2 Part A. So make sure it starts at the origin, make sure that the general shape is right, and in particular it doesn't slam down into this axis here, and then the higher temperature curve shifted this way, flattened, and the activation energy just marked as a single line there. Now when we get into Part B, it asks you to explain how you can use that to explain why the rate of reaction is higher at higher temperature. And there are really 2 parts to that, but one of them, as far as A level is concerned, is much more important. So we'll talk about the first one first, which is actually the less important one, and generally is one that you don't lose marks if you don't mention. But you can see it's an issue that because the average energy of the molecules is higher, the average kinetic energy is higher at higher temperature, what that means is that on average they'll be moving around quicker, and if they're moving around quicker they're going to collide more often, and that will make the reaction rate higher at higher temperature. Okay, so you could say that because it's true, and it is a part of the difference. Okay, that because the average kinetic energy is higher, the average speed of the molecules is greater, and therefore they collide more often, so the rate will be increased at higher temperature. However, that's not the main factor. For most reactions, that's a pretty small contribution to the overall temperature dependence, which is why often there isn't a mark for mentioning it. Much more significant is the fact that when collisions happen, the molecules have to have at least this amount of energy. Otherwise the reaction can't happen. Okay, there isn't enough energy if they've got less than this for the existing bonds to break, and therefore nothing will happen. And you can quantify what proportion of molecules have an energy great enough for a reaction to happen when they collide, because it will represent the fraction of the area that's to the right of the activation energy. So it's a good way to do it is to use shading to mark this on. Remember, you can't use colours in the exam, so shading is a good way to do it, and just indicate that that represents the population of molecules with enough energy to react when they collide, and this is the low temperature curve. So this will be the population of molecules with enough energy to react when they collide at low temperature. And we can do exactly the same thing at the higher temperature, because that's now this curve, and so we can use a different shading, so something like this. And you can see then that there's a much bigger population of molecules, a bigger proportion of the total have an energy greater than the activation energy at higher temperature. Okay, so this is the same but at high temperature. And if you sort of mark that on there, it makes it clearer when you then put that in a sentence what you're talking about. So what that diagram shows, and what you now need to write in then, is that at higher temperature a bigger proportion of molecules have energy greater than the activation energy, meaning that they can successfully react when they collide. Okay, so that's what those shaded areas show you. But you've still got to spell it out more, because they'll say, okay, yeah, this bigger proportion of molecules have got enough energy, but what does that mean? So you've got to spell it out. This means that, therefore, successful collisions will occur more frequently. Okay, because if each collision that occurs has a bigger chance of success, obviously successful collisions will occur more frequently at higher temperature. And again, spell it out even more, because they'll say, okay, successful collisions are occurring more frequently. What does that mean? So you finally spell it out and say the rate of reaction is greater at higher temperature. Okay, so getting full marks in these questions is all about really spelling it out. The danger is that you'll feel that you've implied enough, and they don't do implied. You've got to spell it out like that. So it's worth practicing those things, because you probably have to sort of spell it out more than you may feel inclined to do.